Hello, everyone. Thank you all for joining this stream today. Today, I will be trying to demystify the low latency audio on Android. I'm Nishant Srivastava. I'm an Android engineer working here in Berlin, and I've had the opportunity to work with a lot of startups in the past, which kind of dealt with doing audio processing on Android platform. I've worked with companies that kind of did low latency audio or were also dealing in digital signal processing itself. So during all these different opportunities that I had, I kind of started seeing some sort of a pattern of how Android as a platform has evolved over time when it comes to audio, right? So let's start with something that we want to understand and maybe we all know about is how do you do raw audio processing on Android or basically Java in general, right? So the way that you all probably would do, or anyone if you look it up would do, is that you will have doing Googling, that you will find something called a sound pool, which basically allows you to assimilate all sorts of like sound and then be able to play them around using the sound pool class, right? And then you also have the audio record class that kind of manages audio resources for Java applications. When you're recording audio or when you are recording audio from the microphone of the platform or the Android platform. And then you also have track class, which manages and plays a single audio resource for Java applications. And this is what mostly all the people would do because they are on the JVM side. Kotlin code, you're writing Java code, and this is what you see. But the goal is not that, right? Your goal is that you want highly performant audio. You want audio that performs really well. When I say that word, actually, what I mean by that is that the audio is highly responsive. Imagine being a situation where you kind of speak into the microphone of your phone, and then it takes a bit of a time to go on to the other side when you're in a call. That's not a responsive audio. But if you were to do it, say if you speak in your microphone and then you output the audio right away from the speaker, that's a highly responsive audio. Typical examples of this would actually be like synthesizers, which kind of synthesizes audio. And it is the one that handles all the different sections when it comes to like creating audio, right? So these are synthesizer applications that you would have on Android. Then you also have drum machines that kind of plays drum sounds when you hit a certain view, I would say, widget. It's like drum pads, as you can think of. You have karaoke apps, you have metronome apps, DJ mixing apps, audio effects, and obviously in a game, imagine you shooting something with a gun in, say, a particular first-person shooter game, and then the audio comes a bit late. That's not good, right? So you want highly performant audio there too. And obviously, there are many cases for this. The important point here is that to achieve this on Android, we have access to two libraries. The support comes from something called OpenSL ES. It's a very native layer. OpenSL ES basically stands for Open Sound Library for Embedded System. It has been the standard for a very long time. So from Android Gingerbread until the API 26, that's Oreo. This is what existed for a very long time. But for an app developer, it's a lot of boilerplate code. You have to write a lot of code to be able to work with this API. The other option that you actually have is called AAudio, which I wouldn't say has a full form here, but I like to call it advanced audio. It's basically a lightweight alternative to OpenSL ES. It was kind of introduced in 8.0 or API 26, but it actually became usable on Android 8.1 onwards. That is API 27 onwards. And we'll talk about why that is the case in the next few slides. But the core problem here is something else, right? We started with something that we want to understand, and there are many terms that we'll be using in this talk itself, right? And I will try to demystify the problems that Android as a platform has on this. So let's talk about low latency audio. And I like to look at this by breaking this down. So the first thing that we need to understand is what is latency. the way I pitch this forward is that I think latency is mostly delay that we're talking about in the most simpler format, right? The actual definition, though, is that it takes the amount of time it takes for a signal to travel through the system. A good example is touch latency, as we call it, is when you touch on your smartphone right now, the amount of time it takes for you to touch the screen and then the signal to go into the device and be registered as a touch to generate a feedback is your touch latency. That's the amount of time it's taking. And if you add that to an audio latency, that becomes an audio signal based time that it takes to travel through the system. But how is that possible? Like, why would you have audio latency, right? That's a bigger question in the room. And that in that sense, what we need to understand is that audio in itself needs to travel through different components in a system to be able to be delivered through a speaker, right? So imagine your audio being actually recorded from a microphone, that is analog signal, needs to get converted into digital signal. And then when it is supposed to be played back, then the digital is converted back to analog. That is your audio interface latency. The amount of time it took for all of this processing from analog to digital to analog is an audio interface latency. Obviously, you could want to add some sort of an effect in the process, and that would be your digital signal processing here. And this could be you adding some phase effect, echo effect, reverb effect, and that's your digital signal processing latency, because the amount of time it will take for this processing is going to add to this total time for audio to be delivered out from the speakerphone, right? And then some of these other bigger units that they probably run outside smartphones, but they do run Android, they do have this extra path that they have to travel through cables. There is some sort of a mixer in between. And then you also have hard drives on which basically it takes a little bit of extra time to maybe process some data and get that back out and then push it out to the speakers, right? So all of that contributes to the audio latency. What this basically looks like on some of the devices when it comes to Android is that here's a simplified version of something like that. But if you want to check the complex version, I added the link at the bottom of this slide. You can check that out later. But the general process is that you register some sort of a reaction from your application framework. You trigger some sort of an event, and it needs to go through a JNI layer because you're on the Java side and you need to go to the native framework now. JNI stands for Java Native Interface. And after going through that, the native framework kind of starts sending the data in binder messages. So it talks to the media server. And once the message is received on the media server kind of talks to the HAL, which is your hardware abstraction layer. And then the HAL goes in and talks to the drivers that are in the Linux kernel. The whole process is managed between the media server and the native framework. And then the event is triggered back to the application framework based on the callback that we have set up. So because we're talking about audio latency, there are many types of audio latency that we need to understand. There's output latency that is the time that it takes for an audio sample to be generated by an app and then played, and then it's like output through the speakerphone, right? And then input latency is your analog signal going through the microphone of the phone and then being processed by the application. So we're talking about many kind of latency in this process. There's a round trip when you add output and input at the same time, and that's your round trip latency. And then there's a warm-up latency that happens when you are starting up. So the way that audio is actually processed on an Android device is that you have a buffer, or sort of think of it as array that starts to get filled up before it can be processed as a full audio signal, right? But in the very beginning, the array is empty. To fill that up, it's going to take up a little bit of time. And that is your warm-up latency. That's the amount of time it's taking for the audio to actually start getting processed. And that's why there's a warm-up latency. Now, what this brings up as a key point here is that we cannot get rid of latency from the systems. It's not possible. There's going to be some sort of a latency in the system because the signal needs to travel through the board. It needs to get processed in the system and also needs to react to certain things. What it can be done is that it can only be minimized to a certain point so that it is not as much noticeable. So taking that into account, certain standards have been set around, right? So one of these standards is that if the round trip latency, that is your input and output trip that it takes for the signal to travel, is less than 10 milliseconds, then that's considered professional grade audio. When the latency goes beyond 20 milliseconds, then it's perceived as a lag for the user. But this is the general landscape that we are talking about. Let's look at the audio latency on other mobile platforms also. Because we are comparing Android as a mobile platform, let's look at iOS, which kind of uses compiled code. It uses Objective-C, it uses C, C++ if required, and also uses Swift, and compiles down the whole code to machine level code as much as it can. So the latency there is almost around 7 to 12 milliseconds. Really good. For Android though, when it comes to flagship devices is when you actually get like 15 to 20 milliseconds. But for older devices, the time is around 400 plus milliseconds, which is really bad. To get an idea if a device supports a certain kind of a functionality for low latency or like a pro audio as we call it, we do have functionality in the JVM or through the Android SDK. And the way you do that is that you actually ask the package manager for the system feature that it supports. And this is basically set by the AOSP and the OEMs. Tell you, oh, so this device supports pro feature, and then it supports like low latency. But not everything is good, right? So this is where things actually start to happen in a bit different way. And we are not gonna dive into the problems that are on the Android platform. So the very first thing that we need to understand is that we have really bad latency for Android for a very long time. And we struggled for that for a very long time. To bring this into perspective, let's look at the bug tracker for Android. So this bug issue was created that add API for low latency audio in 2009, August 1, 2009, right? And this was for AOSP version 4.0, which is like pretty old. We don't even remember that anymore, right? And then certain information start trickling in, and this was like almost, I would say, 5 years from now, from 2009. In 2013, where people started talking about high performance audio. Keep in mind, no one is building high performance audio apps during this time for Android because it's not possible to do that, right? In 2017 is when we start talking about AAudio, a new C API, which simplifies the whole process and allows you to do low latency audio. This is June 14, 2017, almost 9 years, right? When it comes to like in 2018, this whole issue was marked as fixed because now it was made clear that there's OpenSL ES and there's an AAudio API. We should be using that. Let's close this down, and then in future device specific support, we'll start providing that. This is 2018, almost 10 years. The question here is that why did it take 10 years, right? Well, the problem attributes from many different areas here. The very first being that we have OS level problems. Let's look at AAudio for that particular piece, right? So AAudio in general was released in 8.0 API 26, but it couldn't work with 8.0 because 8.0 itself had a reference counting issue, which would cause a crash after the stream was closed. So you open a stream of audio and you start listening to this, but when you go on to close the stream, then the crash occurs. So this is one of the reasons that AAudio is suggested or recommended is to be used after API 27 onwards. We have OS level problems for CPU scaling, which is basically that when OEMs kind of like modify their Android version, they try to do it to maximize the battery performance, right? So they try to reduce CPU frequency by using a CPU governor, right? And when they do that, what basically means is that your CPU is not processing enough information because the frequency is reduced from say 3 gigahertz to say 1.5 gigahertz. It's almost at 50% duty cycle, and then it's not able to process as much audio. And this kind of causes a lot of problems because the audio that is streaming through the process is not getting processed quickly enough. So the CPU starts to drop some of them. And then you hear these glitches in audio when you're trying to get a very responsive audio. And the CPU scaling in general, the way that people started to fix this is by adding a certain hack. You can see this in the Google samples repository. Don Turner, who's a big engineer for this, who's pushing for the high performance audio, started mentioning that people are using fake touch events to avoid CPU scaling. Basically, triggering a touch event every few seconds so that they can keep the UI alive and sort of like make sure that the CPU understands that some sort of a user interaction is happening. So its high performance mode is always active. Although he later on said that it is considered harmful as an hack and it should not be used, but I can tell you that a lot of companies actually still use it because there's no way around it. It's an OS level problem and the CPU governor is kind of scaling everything down. Let's also look at API level problems here. And the key term here is the sample rate. So when I talk about sample rate, the way I like to describe this is that how often an analog signal is chunked or sampled per second. It looks something like this. You have a waveform, a signal, and then you start chunking it into different chunks, as we call it, right? When you do it in 1 second and you do it 44,100 times in a second, then we call it the sampling rate of 44.1 kilohertz. And this is how it came down to, for CDs. The original analog signal is basically sampled 44,100 times per second. So it's 44.1 kilohertz for CDs, right? For DVDs, although it goes a bit higher and goes to 96 kilohertz and 192 kilohertz, which is a pretty high one. What you need to see here, though, is that higher the sample rate, you require more storage space to do this chunking. And then there's also obviously more processing that needs to be done. The splitting of the audio signal into more sample requires more work to be done. And this is a big problem because not all devices are capable enough to chunk audio in all these sample rates, right? And as a developer, we don't know what is the sample rate anymore. So we kind of have an hack. Internally, what we do is we try to initialize an audio record class with a certain number of valid sample rates, and we iterate over them until we get a valid one. And the way that we do this is the reason being here is that these sample rates vary by devices. Some devices would report 1600, some 16,000, and some of them would report 44,100. And it varies a lot. So the only better hack is to actually do this. The other API level problem that we have is the buffer length. And it kind of stems from the same kind of a thing that a sample rate has, is that buffer length in general is represented by how much of the audio data that is ready to be processed, right? But as a app developer, I don't know what the devices can support. We don't know what is the buffer length to use, right? In ideal scenarios, this buffer length would be a power of 2, but devices I've seen would report multiples of 8 2, right? So it's a power of like 3 times 2 or 4 times 2, and that's really bad. So another hack that we kind of use a lot is something that's very similar to the sample rate one. As I was saying, you kind of initialize the audio record class, and then you check, was it initialized properly? And we do that with a certain set of valid buffer sizes. If one of these buffer sizes fails, then we just discard it and try to check it with the other one. But that's not all. This is not the limitation we are talking about. We are talking about Android as an operating system, and that operating system also talks to other devices. So at this point, I want to bring in the problems with Bluetooth. So understand that Bluetooth has its own standards, right? And Android has a complex audio path in general that we already saw up till now, right? It has its own issues, but Bluetooth, because it has its own standard, it has other conversions that it needs to do before it sends it out to other devices. These two latencies add up to generate a much higher latency. To look at this, we need to understand how Bluetooth actually is kind of working with audio. What it does is it takes the audio stream and it uses a codec format to convert to something that it can process and send over the Bluetooth standard way of sending things, right? It requires more buffers, and it also needs to package and queue these packets before it can send it to Bluetooth. The research that other people have actually done on this is that they have kind of measured with what kind of a codec, how much is the latency, right? And it's been observed that the latency can go to 500 milliseconds, or it could be around like 200 milliseconds in a standard test of how the audio is going over Bluetooth, which is really problematic in this case because you cannot build apps that do 200 milliseconds, like a huge lag for people to use, right? So in this case, you will notice that Pixel 3 XL is kind of hitting like 200 milliseconds around, and Huawei Mate 20 Pro is kind of hitting 500 plus milliseconds. And that's really bad. And we see this problem quite often when it comes to Bluetooth, although Bluetooth quite recently came up with a new standard, and hopefully that's going to fix things for Android too, with time, with more flagship device. What this has actually trickled down to is that we need to understand how we want to work with native audio here. We want to work with high performance audio, and to do that, we want to require the fastest path it is available for us to trigger or take an input of an audio signal and then output it out from the speakerphone, right? To do that, if we did it through a Java version, we have a problem because it adds an extra layer in between. The code executes on JVM. There's not good APIs to work with. But what is much easier to work with is the native code, because native code in general is completely like it's pure math. It's basically doing some sort of calculation algorithms, and it's mostly portable code. So when you kind of deploy this and you move it to different other platforms, it's much easier to manage and maintain. At the same time, what is also important is that the native code also talks directly to the HAL of the OS, the hardware abstraction layer of the OS. And obviously it's a compiled machine code, so it runs much easily. So does that mean that you as developers need to write native code, like all the boilerplate and everything? Well, for a certain long time, we had to do it. But then Donton and his team basically built something called Oboe. And Oboe, by the way, means it's like an instrument that takes it's like a wind instrument, and you blow from one side, it comes out, the sound comes from the other side. But Oboe in general is basically a C++ library, which makes it easy to build high performance audio apps on Android, which is great because now it's like a wrapper that will handle a lot of these edge cases for you. So Oboe is kind of open source, is compatible with 99% of devices, works with API more than 16, is decoupled from the OS releases. That's the best part. Has automatic latency tuning. It can tune itself to get the least latency in the audio, and also is handling a lot of platform and manufacturer specific works. Obviously, it's an NDK based library, so it uses in JNI. And the way that it actually does this is that it bifurcates. It's like a wrapper, right? And it understands what API this is being run on, and it goes to OpenSL ES implementation of this thing, or for 16 plus devices, API 16 plus, and goes to AAudio for APIs 27 plus devices, and kind of provides a very nice clean API to work with. If you were to try including this, by the way, today, there's an experimental way of doing this using prefab. You can do it of saying implementation, Google, Oboe, and give it a version. You do need to enable prefab because it's not enabled by default. You need to set these flags in your Gradle.properties file. Also, you need to add some things to your CMake.txt file. But I'm not going to cover that part right away because it's like a lot of technical and native code. And obviously, we don't have enough time to cover that part. But what I will tell you is that this experimental thing I've been trying for some time, it kind of doesn't work as much. So what people actually use mostly is that they clone the repository and they edit their CMake list.txt file, and they reference the directory directly to compile this code that they've cloned. And then they refresh the Link C++ project and basically just start writing Oboe code. As you can see, Oboe code is pretty much simple. You have like very simple builder pattern. You have something where you can say create playback stream. You can define a builder, and then you can set the performance mode. As you can see, low latency. You can set the format. You can get a callback, and obviously open a managed stream here, which is super nice. It's not all of the code, but it is the important code that most people would have to write. And this is it, compared to what OpenSL ES code is, which is mostly all of this. I had to shrink down the last third column so that I could put more code in there. But basically, you can see it does the similar kind of stuff. It creates an engine, output, sound mixer, kind of mix the output, clears the sound, formats the data as we were talking about earlier, and then also is like trying to do some sort of like combine the format into the source. Bunch of stuff that you shouldn't care about because Oboe is already doing that for you. An important point to note here is that while we are talking about the sample rate problem, is something that Oboe quite recently fixed it. With version 1.3.0, they now enable you to convert the audio into a sample rate that the device supports. And it basically allows you to get the low latency audio right away without having to do a bunch of things. But it is opt-in. The reason it is opt-in is because this involves a certain CPU overhead, and we don't want to like impose this on developers, right? So that's why you basically tell Oboe that if you don't get the fast path, then you should go on to convert the sample rate, the channel, and the format. And all of these conversions are allowed. Just go ahead and do it and give me the fastest path possible. The other problems that we have already seen in native code in general is that you have to deal with the raw pointers and everything. As you can see, the asterisk stream builder and then doing ampersand stream builder is like dealing with pointers. And if the pointer goes out of scope and you try to access it, you have a crash, you have a set fault or some sort of like a dangling pointer problem. But Oboe quite recently also fixed that. They now give you something called manage stream. And this basically makes sure that once the scope is complete, then the stream is no more accessible and you can't access it anymore. It takes care of all the extra things that you will do on your own. Obviously, creating all these samples and everything is pretty hard for people to put it out. What Oboe has already done is that they put out pretty nice samples out there. And I will probably try to demo one at the end of my presentation for other people that I have on my phone. Oboe also is suggesting to use a sort of an tester app that they have in the repository. And what it allows you to do is to test against your device and figure out the device latency and glitches. It is just a way of testing things. It just helps to debug Oboe problems or any other problems that you would have. But it's a good tool to have in your tools set. But Oboe is not actually like perfect. There are a couple of things that we need to take into account. And one of those is that Oboe is not thread safe. And you basically just cannot concurrently call 2 more threads and do audio processing. It actually kind of recommends you don't do that because it avoids using mutexes. And the reason it's trying to do that is that if you like do context switching with threads and you do preemption, then you get this audio glitch, which they want to avoid, right? A lot of actually apps are using this in production. Juice, which is basically a C++ framework. They are partially open source, cross-platform. Obviously, you have desktop and mobile applications. You have a version 5.3.0 added support with Oboe for Juice, which is pretty nice. Your G-Stomper rhythm, which you can use also, is using under the hood as Oboe. Pretty nice app. You should try it out. And our very own Berlin-based company, SoundCloud, also uses Oboe. There's a link at the bottom of this slide, basically where they talk about how they implemented Oboe and they started using it in their application. And then there are a bunch of other applications with pretty good downloads, more than 1 million downloads. You have Music Speed Changer, N-Track Studio, and a bunch of these that allows you to do that. But there's one more con that I do want to mention. This is more at the end of the guide that they publish. This is sort of like a known issue, and I don't think so they plan on fixing it, wherein you don't have some functions implemented. This is mostly done because this is not required up till now, right? So trying to use something that OpenSL ES already did doesn't make sense. So maybe what they are doing is that they're kind of using this from the setup itself, right? And at this point, I actually want to maybe demo a sort of an application that I have. So this one is called WaveMaker. You can definitely search it up. There's a code lab for this too. The code lab is outdated, but this will work for other people too. But what's going to happen is that I have an application open that when I tap on it, it kind of generates an audio instantly. So when I will tap on it, you might hear my fingernail first and then the audio. But it will happen so fast that this is the high response audio as we are talking about. So for example, I'm going to tap now on this one. Hopefully the audio comes in. Okay. Yeah. And there's another application that they have called Hello Oboe that is in their samples. And this one also does the similar kind of thing, but it also shows you the latency value. So I could do the same thing on this one too. So as you can see, the fingernail sound that you hear, as well as the sound that you're hearing of the application responding back, is near about very near to each other. It's highly responsive. The latency on the phone, by the way, is around 20 milliseconds. When I run it on my Asus, it goes to around like 6 milliseconds. On Pixel 3a, it goes around like 9 milliseconds. So we are doing pretty good when it comes to the current setup for Android comes. And I guess that's all of it. So I would probably open up the session now for questions if you have any. And I'm going to share my screen for this. If people have questions, please ask. Okay, so we have a question. How hard is it to implement a low pass filter with Oboe? So keep in mind that Oboe in general is just handling the API level code for you. It's not gonna be doing things related to creating effects or filters or any of this sort, because all of the things that you're talking about doesn't need to care about what Oboe does, right? Oboe is kind of simplifying how you how do you actually access the input and the output. So Oboe has a couple of terms that we can talk about. It has audio stream, audio devices, and the way that it works is that it basically just takes the audio stream and pushes it out to the audio device. It could be a sink or a source. Source would be an input, a sink would be an output, and it basically does that. Your low pass filter code, though, is purely C code, which you could probably get it from some sort of another library. And Oboe doesn't care about that. What Oboe does care about is that you are able to process your audio. So it will give you access to the audio stream. And then you can pass that audio stream through your low pass filter via some other library that you have. You have some C++ library, something called KissFFT. There's some that allows you to do low pass filter, the high pass filter. There's Chebyshev filter, other stuff also that you can basically kind of just write in C yourself. So making it very cross-platform way of implementing things too. You probably don't want to use Oboe thinking that it will allow you to write standard math-based filters. Because it doesn't require a framework to work with. It is very clean, it's very small in that sense, and that is one of the reasons that it works with things. I hope I answered your question. Okay, if anyone else has any questions. Okay, so the next question I have is for, would you have production data on latency you could share since it seemed to be device specific? So, okay, so maybe the follow-up question on that is that what kind of a latency are you talking about? If you're talking about device specific latency for just the audio that plays in and not Bluetooth-based latency also included, then you can basically, the version that most people would do is that there are a couple of companies that are actually doing a lot of tests on this. So one company I know is called Superpowered, I think. And they have their own SDK. They try to pitch that they are much better than Oboe. But Oboe is actually not trying to be like Superpowered as a company is doing, right? So Oboe is completely different. It's a different layer. But what you are asking for is someone who has gone through multiple devices and tested them against how much latency there is when an audio goes through a round trip scenario, right? So Superpowered kind of has public pages that you can search. It is also in my slides where you can get the link. There's the superpowered.com/latency, and basically you can go there, and they have published quite a lot of devices and against them what is the latency that they have observed over a period of time. And then they go on to say that they kind of fix that with their SDK because they do some sort of other NDK stuff. But if your idea is to understand what is that latency, that is one good point to look at their pages, the latency related graphs. And the second one is that, as I said, Oboe has a tester app, and you have a set of devices with you. Then you can run this app and then simulate the tap thing that I was doing on the device. And as you do that, there's a latency feed or like a text view that kind of updates as soon as you do it, and it shows the latency. So this is why I know that my Asus Zenfone 6 has a latency around 6 to 7 milliseconds. On my Xiaomi Mi A1, the latency is around 20 to 21 milliseconds. And you can see that. So you could compile some of your data too, but having to do it against other people's devices is something that not many people publish it out. So it's all usually governed by companies, CLA and other stuff. Hope that answered your question. Does anyone else has any questions? Okay, I think we are done with the whole presentation now, and I hope that if you have any questions, you reach out to me on the Slack channel, and I'll see you guys in the Slack channel. Thank you for being such a good audience, and I think we're done. So bye-bye.